Hello everyone and welcome back to Diksha Karnataka YouTube channel, and you are watching PU2 Brahmastra series where we are trying to help you to achieve maximum possible marks in your upcoming second PU exam. And today is day 12 and today's day is for physics, right? So we are going to discuss moving charges and magnetism chapter. Also, if you have not joined our WhatsApp channel, don't forget to join our WhatsApp channel. The link is given in the description. There we are every time we are publishing a new topic, new video, new content, that you will get updated on our WhatsApp channel. So I request everyone to join our WhatsApp channel. Now come to today's topic. We are going to discuss, today is Friday, so physics, moving charges and magnetism is going to come, and as you know, all the chapters before are already completed. So chemistry, physics, biology, chemistry, these chapters are already completed, and tomorrow Saturday will be continuity and differentiability part 1, sexual reproduction in flowering plants, that will be biology chapter, and then in maths, continuity and differentiability part 2 will be there. So without any delay, let's look into the 3 blueprints that we have received from your PU board. Okay, you can download the blueprint from PU board website. So let's see first MCQ questions. Okay, from the first blueprint we can see the MCQ is a remember based question, so we know that remember based MCQs are easy, but in blueprint 2 and in blueprint 3 we can see that the MCQ is HOTS question. So HOTS question means it's slightly a difficult question, higher order thinking skill, so that's why you have to use your thinking skill, you have to use your brain to solve such questions, so that's why it is slightly difficult. Okay, now no fill in the blanks in this chapter as well, and a small answer type 2 marks question is so as you can see in blueprint 1 and blueprint 2 they have given understanding based, and in slash new term NP is written. What is the meaning of NP? So basically they are saying that 2 marks numerical questions will come. Okay, so 2 marks numerical problems will come, so that's why this is a unique chapter where you can expect that 2 marks numerical question, and this is there in 2 of the blueprints, so highly probably there will be a numerical question from this chapter, right? And in the blueprint 3 it is simply an understanding based question, so maybe if you are getting blueprint 3 for your final exam, then maybe they will give you question based on understanding, not only writing. Okay, we will discuss everything. Okay, and as you can see in small answer type questions, 3 mark, there will be 1 remembering question, 1 understanding question, 1 remembering question. So most probably on an average you see that 2 of the 3 is remembering questions, so where they will give you some theory and they will ask you to write it down, and maybe in some cases they will ask you some understanding based question. Long answer type questions, so you can see 2 of them are application, 1 of them is understanding, so this will be basically writing question. And most importantly, very good news for all of you, there is no numerical questions of 5 marks from this chapter, but there will be a 2 marks numerical questions from this chapter. Okay, so if you are someone who can mug the concepts well, you remember the concepts well, but you are not so good in numerical problems, then you can skip the short answer type from this chapter. You focus on 3 marks and 5 marks question. Okay, and there is no other 5 marks question numerical problem from this chapter, so it will be easy chapter. But as you can see, the weightage wise it is 11 marks from all the 3 blueprints, so definitely it's a very, very important chapter, right? As I said, if 10 marks is in a chapter, that will be a very important chapter. Okay, more than 10 marks is obviously very important chapter. There are few chapters where the marks are less than 10 marks, so we will discuss that in our later half of the Brahmastra series. So right now we are only discussing the most important chapters, so this comes the 4th chapter of our series. So what all we are going to discuss today? We are going to discuss 1 to 15 MCQ questions, 16 to 20 small answer type 5. Okay, 21 to 20, here slightly change is there, 25 to 26 will be your small answer type 3 marks question, so there will be 6 3 marks question, and there will be 27 to 30 will be long answer type question, so there will be 4 long answer type question. Okay, not 5, 4 long answer type question, because I have checked all the years previously. I thought I will give you 5 long answer type questions, but after checking all the previous years, mainly 2 questions are coming almost every alternate year. Okay, I will discuss obviously those 2, and once some other question came, I am going to discuss that as well. And in your latest blueprint, one of the blueprint has some question which never came in your previous years. We are going to discuss that question as well. So 4 previous year 4 questions which may come in your annual exam from this chapter. All 4 questions will be covered in this lecture, and there will be a note that which 2 are very, very important. That 2 you cannot miss. Other 2 is optional for you. Okay, so first start with the MCQ questions. A moving coil galvanometer can be converted into a voltmeter by connecting. How can you convert a galvanometer into a voltmeter? Okay, let's see the options. A low resistance in parallel with the galvanometer, no. A low resistance in series with the galvanometer, no. High resistance in parallel with the galvanometer, no. High resistance in series with the galvanometer, yes. Okay, so for galvanometer to voltmeter, for galvanometer to voltmeter, you have to add high resistance in series. Okay, for galvanometer to ammeter, you have to apply a resistance in parallel. Okay, this how you can remember this. Okay, voltmeter is where you apply series resistance, high value. Okay, for ammeter you apply low value resistance in parallel. Okay, now question number 2. So there are few questions that you have to match the columns. Okay, physical quantities related to the magnetism are listed in column 1 and the dimensions are listed in column 2. Identify the correct match. Okay, so first let's see what are all the options, and then we will discuss what are the probable answer. Okay, so magnetic field, magnetic permeability, magnetic moment. Okay, so what is we will start with the easiest one, that is magnetic moment. Okay, so magnetic moment is IA. Okay, magnetic moment is defined by the term I into A. I is current, I is current, yes, and A is area. So its unit is L square A, dimension basically. Dimension is L square A. L square is from area, I is unit. So don't get confused with the terms and their dimensions. Okay, I's dimension is A, whereas A's dimension is L square. Here A represents area. Okay, so don't be confused. So L square A is the magnetic moment of this. So first we will see option 3 must be equals to B. Okay, now in some cases you can check if there is only one case where option A is equals to B is given or not. Okay, so even if you don't remember the magnetic field dimension, even if you don't remember the magnetic permeability dimension, okay, what you can do is you try to find this is a trick that I am going to teach you. Try to find the easiest one to remember. Okay, M is equal to IA, the easiest way to remember for the given case. They will give you any such combinations. Okay, any such combinations, and whatever you remembered. Okay, try to find okay, this one I remember, this one's dimension is this. Now check the options if any one of them actually matching with the given option or not. So as you can see in the option 3 is matched with B only once. So only one. So without any calculations you can simply close your eyes and you can mark definitely this will be the correct answer. Also one more trick, since you have calculated magnetic moment matches with B, so definitely you can say that magnetic field, obviously they will not give direct combination, so this should be here and this should be here. This is another way to guess. Okay, even if you don't remember that magnetic field's dimension is mt to the power minus 2 a to the power minus 1, okay, or magnetic permeability, in fact I also forgot the magnetic permeability dimension, mlt to the power minus 2 a to the power minus 2. You cannot remember all these dimensions, you have to remember the formulas. From the formula you can find the dimensions. Okay, that is one thing. Otherwise you can find whatever quantity you find it easier to remember, and from there you find the given dimension, and once once you find the dimension, you check what all are the options where they have these options are matching. Now in this case only one option where you are getting this combination, so definitely this is the correct answer, no doubt about it, right? So this is the easiest way to solve without doing too much mathematics, without putting your head. This is a hot question obviously, so you have to answer such questions. Next question. A charged particle of charge q is moving in a uniform magnetic field. The angle between the velocity v of the charged particle and the magnetic field b is theta. Okay, so angle between v and b is theta. The trajectory of the charged particle varies with the angle theta. We know that. Match the following table by choosing the appropriate trajectory traced by the charged particle to the different possible values of angle theta. So they have given you a few options. Angle theta equals to 0. Now theta equals to 0 is basically when it is a straight line. So theta equals to 0 is straight line. Theta is equal to 19 is circle. Okay, theta is equal to 90 is the circle. We know that theta is equal to 0 is straight line. Obviously there is there will be no deviation in that case, right? And theta equals to 45, any angle between 0 and 90 will be a helix. Okay, so any angle between 0 and 90 will be an helix, so definitely this is an helix. So we can, in this case we can match all the cases, but in case you are confused about 45 degree, you know that for 0 degree it is a straight line, for 90 degree it's a circle. So you can based on these two concepts you can find okay what will be the third one. Now let's see the answer. For 1 it will be C. So for 1 it will be C. So obviously only one correct answer is obviously here also. For 1 it is C. For 2 it is B. No, it is not correct. For 3 it is A. Sorry, my mistake. So 0 is matches with C, not B. So 0 is matches with C. 45 is 0 is straight line, 45 is helix, and 90 is circle. So 1 is matching with B. So 1 is matching with B. So there are two options where 1 is matching with B. Okay, so you have to see which one of them is correct. Now 2 is matching with C. So 2 is matching with C and 3 is matching with A. So this is the option. Okay, definitely this is the correct answer. So option B is correct in this case. This is also a hard question. Be careful. Okay, so what you can do is that instead of doing this, you can use different colors to mark them. Okay, 0 is straight line, 45 is helix, and 90 is circle. Okay, so this will help you to remember which one you have corrected. If you use same color, it might be difficult. Or what else you can do is you can mention this is B number 2. This is number 1 and this is number 3. This is another way that every student uses. You can do it this way also. So 3 is A, 1 is B, 2 is C. You can see only this option is correct, right? Now next question. The Lorentz force is the force on a charged particle moving in a region containing only electric field, only magnetic field, both electric and magnetic field, only crossed electric and magnetic fields. It is both electric and magnetic field. Okay, there is no, there should not be any relationship between electric and magnetic field. For example, they have said cross. Cross means electric field is in this direction, magnetic field in this direction. But it is not necessarily true. Okay, even if the electric field and magnetic fields are parallel, Lorentz force is still applicable. Okay, Lorentz force is only when magnetic and electric field both are present. In case one is present, another one is absent, that is a special case obviously, but that force is also Lorentz force. Okay, so whenever there is a force acting on a charged particle moving in a magnetic and electric field, then it is a Lorentz force. Okay, force on a charged particle moving in a magnetic field is maximum when the angle between the velocity of the charge and the magnetic field is. So force on a charged particle on a magnetic field is maximum. So what is the force on a charged particle? Q B V sine theta. Okay, so force is maximum is when theta is equals to 90 degrees. Okay, or theta is equals to 180 degree can be possible as well, but because it says only maximum, okay, it is 90 degree, 180 degrees minus. So magnitude wise, since they have not mentioned magnitude, so only 90 degree is the correct answer. Okay, if they said that when it will be most unstable, then it will be 180 degree. Okay, at 180 degree it is most unstable because the force is negative, right? Now, a charged particle is released from the rest at a region of uniform magnetic and electric field parallel to each other. The particle will move in a. So, what is the question? We have a magnetic field and we have an electric field. Okay, both are parallel to each other, and what you have a charged particle just released at rest. Now what all are the forces will act on it? Okay, so first of all, because it is at rest, magnetic force will be 0. Okay, initially electric force will act on it. Electric force will be Q times E, right? So the particle will start accelerating in this direction, in the direction of electric field, positive charge, right? If it is negative charge, it will move in the opposite direction. But in that both cases, okay, the angle between magnetic field and electric field will be 0, right? So the angle between magnetic field and electric field will be 0. That means the particle will not experience any magnetic field, so it will move in a straight line, right? If the angle is 90 degrees, it's a circle. If it is 0 degree, it will be a straight line. If it is any angle between 0 and 90, then it will be an helix, right? So only straight line is possible. Now, next question. A galvanometer can be converted into voltmeter by connecting high resistance in series, high resistance in parallel, low resistance in series, low resistance in parallel. So similar question. Okay, a galvanometer can be converted into voltmeter by high resistance in series. Okay, previous year question, so maybe some questions are repeated, but this is also order is different. So as you can see, high resistance in series is the correct answer. Next, the dimensions of magnetic moment is. So dimensions of magnetic moment, if you remember, I have already discussed magnetic moment is current times area. So current is A and area is L square. So dimension is AL square, or yes, L square A. So L square A is the correct answer. So you don't get confused with this. This is the correct answer. L square A. You have to arrange it. It will be L square A. Okay. So L square A. L square A and LA square both are very close to each other, but actually L square A is the correct answer. Don't get confused. Next, a current I flows along the length of an infinitely long, straight, thin-walled pipe. Then the magnetic field at all points inside the pipe is same but not 0. B at any point inside the pipe is 0. C is 0 only on the axis of the pipe. D different at different points inside the pipe. So we have a thin wall pipe, infinitely long. Okay, pipe means like your water pipe. Okay, so it's a thin walled conducting pipe and current is flowing through it. Okay, I current is flowing through it. Now they have asked you what is the magnetic field inside this pipe. Okay, to find the magnetic field, what we have to do? We have to construct an Amperian loop. If we construct an Amperian loop, we will see that current through this Amperian loop is 0. So if the current through this Amperian loop is 0, then definitely the magnetic field will be 0. Okay, we know that B dot dl equals to mu naught I enclosed, similar to that of Gauss's law, right? So now I enclosed is 0, so definitely this is 0. No current is enclosed here, all the currents is passing through the surface, right? So as long as you are inside the pipe, current cannot be enclosed, so current is 0. Now dl cannot be 0, dl is a length, so length is not 0, this is the length, this is 2 pi r, so dl cannot be 0, only possibility is B is 0. Okay, so magnetic field inside the pipe is 0. So correct answer is option B. At any point inside the pipe it is 0. Okay, next question, question number 10. Parallel currents dash and anti-parallel currents dash. So parallel currents attract and anti-parallel currents repel. Okay, so attract and repel. You shall have to remember parallel currents. When the current is flowing in the same direction, they will feel attractive force. If the current is flowing in the opposite direction, they will feel repulsive force. Okay. A planar loop carrying current I having n closely wound turns and an area A possesses a magnetic moment where magnetic moment is given by NIA. Okay, magnetic moment normally is IA. But if it involves a loop of multiple turns, then it is NIA. Okay, National Investigative Agency. Okay, that investigate any terrorist activity. So that is the NIA. So this is basically magnetic moment. Next question. A charged particle is moving perpendicular to magnetic field. If its speed increases, then its radius. Okay, so very interesting question. A charged particle moving in a particular direction, that means mv square by r equals to, this is the centripetal force, that should be equals to force, magnetic force. What is magnetic force? Magnetic force is QVB. Assuming that the angle between them is 90 degrees, so QVB, circular motion, obviously angle will be 90 degrees. Okay, so radius is mv square divided by QVB. Okay, so R equals to mv divided by QB. One of the v is cancelled, right? So as you can see from the expression for radius is directly proportional to velocity. So if velocity increases, radius will definitely increase. If magnetic field increases, then radius will definitely decrease. Okay, so this is the formula that you have to remember. In case you don't remember, you can use this concept to find what is the relationship. You get enough time to figure this out, right? This is not a competitive exam, so you get some time. In case you are out of ideas, out of context, then you can use your head to find what is the exact relationship, and from there you can say, in this case, if speed increases, the radius will definitely increase. Okay, question number 13. An electron is traveling horizontally towards east. Okay, so an electron is traveling horizontally towards the east direction. This is east. Okay, a magnetic field vertically downward direction exerts a force on the electron. Okay, magnetic field is acting in this direction, vertically downwards. This is east, this is west. Now north and south is like this. Okay, so horizontally means east, west, north, south, right? So north is like this, south is like this, and vertically downward is north, south. Okay, so remember that vertically downward does not necessarily represent south direction. So when you are finding the direction, if you point your hands towards the east, okay, then your face will point towards the north. Your this side will be point towards the west. Okay, east, west, north and south, right? This is the way you should remember. Okay, now as you see, this is the force acting on this, and we know that particle is moving in this direction. Now this is a negative charge. This is a negative charge, right? So force is basically, we know that force is QVB, generally sine theta. Here the angle is 90 degree, so it is minus, charge is negative E minus q VB. So now this, you have to remember that this force is actually negative in sign. So whenever you find the force on a charge, okay, you can assume that this is the direction, right? For positive charge, you point your fingers towards the velocity and then you move towards the magnetic field. You will see this is the direction of the force, but because it's a negative charge, okay, whatever direction you get, you have to reverse it. So we know that north is in this direction and south is in this direction, so this force will be along the direction of south. Okay, so it will be along the direction of south. Very careful, okay, because they have given you the question based on the negative charge. Okay, for positive charge, whatever law, cross product law, you know that you can apply, but when it is a negative charge, you have to reverse the direction. Okay, so for positive charge, if the charge is moving in this direction, simply you put your fingers like this, you rotate it, whatever your thumb points, that will be the direction of your force, right? But because the charge is negative, so force will be opposite to that of this direction. This is the positive direction. Okay, this is the positive direction, but because the force is negative, it will be opposite to that, and in this case it will be south, right? So that's why they have given an electron. If it is a normal charged particle, you could have said normal charged particle means it is assumed to be a positive charge, so in that case you could have said it is in the north direction, right? This is a little complicated question. You have to understand and then apply, then that's why it is called a HOTS question. Question number 14. The resistance of an ideal voltmeter is. The resistance of an ideal voltmeter is infinity. Okay, the resistance of an ideal voltmeter is infinity, because when it is connected in the circuit, it is connected in a parallel combination, and it should have such a high resistance that it does not consume any current of its own. It can only measure the potential difference across any component in the circuit, right? So that's why ideal resistance of a voltmeter should be infinity. Ideal resistance of an ammeter will be 0. Okay, ammeter is connected in series, so definitely it also does not want to have any voltage drop across its end, so that it does not affect the working of the circuit. So an ideal ammeter will have a 0 resistance, an ideal voltmeter will have an infinity resistance. In a moving coil galvanometer, a current I produces a deflection theta. Then I is proportional to tan theta, I is proportional to theta, I is proportional to theta square, I is proportional to theta root 2. So deflection in a galvanometer, we know that is proportional to the current produced. So basically I proportional to theta normally. Okay, in some cases tan theta is the case, but in this case normal they have not mentioned any type of galvanometer, moving coil galvanometer, theta I is directly proportional to theta. Okay. Now let's look into some 2 marks question. A long air cooled solenoid of 1000 turns. So number of turns is 1000. Okay, turns per unit length carries a current of 2 ampere. Okay, it's a 2 mark numerical question. Calculate the magnetic field at the midpoint on its axis. Okay, long solenoid, okay, number of turns is 1000, okay, current carries is 2 ampere. Then what is the magnetic field at the center? B for a long solenoid is given by mu naught Ni. So what is the value of this mu naught? Mu naught is 4 pi times 10 to the power of minus 7. We already know that value of mu naught is 4 pi times 10 to the power of minus 7. Then in case you forget, you can remember this way also, mu naught by 4 pi, that is the constant, is equal to 10 to the power of minus 7 SI units. Okay, so 4 pi times 10 to the power 7 is the value of mu naught only. Now number of turns is 1000 and current is 2 ampere. Okay, so it will be 8 pi times 10 to the power of minus 4 Tesla. everything is in SI unit, so B will be in Tesla unit. Okay, you can use the value, multiply the value with 3.14, so you will get around 24 per 25, right? So approximately 25 times 10 to the power minus 4, but this is also correct. Yes, answer is given 8 pi times 10 to the power of minus 4 Tesla. So this is the correct answer. Very simple question, one formula based question. Okay, so basically what you have to do, if they give you a 2 marks numerical question, you can actually score easily, because the question will be straightforward, direct, with only formula, one formula. If you remember the formula, put the values correctly and calculate them correctly, you will get full marks. Okay, so no need to afraid, this will be not very difficult questions, easy questions. Now next is a moving coil galvanometer gives a deflection of 10 divisions when 200 milliampere of current pass through it. Find the current sensitivity of the galvanometer. Now current sensitivity is defined by number of division divided by amount of current. Okay, here it is milliampere. Milliampere means 10 to the power of minus 3. Okay, simple. So here it will be 10 divided by 2 times 10 to the power of minus 1. Why 2 to the power minus 1? 2 zeros will cancel with one of the two of the minus 3's. Okay, so only one will be left and it will go up. It will become 100 divided by 2, that is 50. Okay, and unit will be per milliampere. Okay, division, 50 division per milliampere. Okay, so 10 division for 200 milliampere and 50 division will be for per milliampere. So correct answer is not milliampere, my mistake, it will be ampere. 50 division per ampere, we have converted into ampere, right? So answer will be 50 divisions per ampere. Okay, so this is the number of division, this is the amount of current. Okay, milliampere to ampere you have to convert it, so answer will be 50 division per ampere. Okay, got it? Next question, question number 18. When does a current carrying conductor placed in an uniform magnetic field experience maximum force and minimum force? So we know that force acting on a current carrying conductor is given by BIL sine theta. Okay, BIL sine theta. Okay, so during my other classes I told you how do I used to remember this. Bill Clinton was America's president when I was a student, so that time I used to remember Bill. Okay, that's how we remembered Bill. So Bill is basically like this. If you want to remember like something else, then also you can do that. So force between force acting on a current carrying conductor is BIL sine theta. Now when the force will be maximum, for maximum force theta should be equals to 90 degrees. Definitely when the theta is 90 degree, force will be maximum. And minimum force when sine theta is 0. When sine theta is 0, sine theta is 0 when theta is equals to 0. Okay, so maximum force will act when the angle between the magnetic field and the direction of current is perpendicular. So if the magnetic field is in this direction, then current should be in this direction. And minimum when the magnetic field and the current are in the same direction. So in fact minimum value is 0. Okay, and maximum value is BIL. Okay, maximum force is BIL, minimum force is 0. Okay, and this happens when the magnetic field and the current are in parallel direction, and this happens when magnetic field and current are in the perpendicular direction. Okay, so this is how you can remember. Next question. So this question is already written. Write the expression for magnetic force per unit length between two long straight parallel conductors carrying current. Give the nature of the force between the two parallel conductors carrying current in the same direction. Okay, so as we know that force between two parallel currents, so here you have to draw the diagram as well. Okay, IA, IB separated by a distance small d. Okay, then this is the formula for force per unit length between these two conductors. Okay, so this conductor is say A, this conductor is B, very long, infinitely long conductors. So they are coming from somewhere, they are coming from somewhere, they are going to somewhere, we don't know exactly, but dotted line signifies they are infinitely long, right? So this is the expression for force. You have to either draw the diagram or explain the terms. Okay, both are fine. And what is the nature of force? We know that parallel currents attract and anti-parallel currents repel. Okay, we already know that, we have learned that in our MCQ part. So here when the parallel conductors, if they ask you what will the relationship between the force, so force is attractive in nature. When the currents are parallel, force is attractive in nature. When the currents are anti-parallel, forces is repulsive in nature. So I have included both. Maybe in your exam they will say what is the relationship between two anti-parallel currents, and then you will say, sir, you have not taught us anti-parallel currents, you have only taught us the parallel current. So parallel currents, if parallel currents attract, anti-parallel current will definitely repel, right? So that is the nature. Now a galvanometer has a series resistance of 12 ohm and the meter shows a full scale deflection for a current of 3 milliampere. How will you convert it into a voltmeter of the range 18 volt? Okay, so they have given you the galvanometer. Okay, the galvanometer has a resistance of 12 ohm. Okay, and to convert a galvanometer into voltmeter, what you have to do, you have to connect a resistance in series with it. Say a resistance in series we have connected. Okay, now you want a full scale deflection for a current of 3 milliampere. Okay, so full scale deflection means when the 3 ampere current is passing through it, you want the galvanometer gives the so galvanometer has some scaling. You have seen the galvanometer, right? So it has some scaling, so it goes to the maximum position at 3 milliampere current. So the maximum current that can pass through is 3 milliampere. So when the maximum current is passing through this, so the voltage reading should be 18 volt. So when the maximum current is passing through the voltmeter, the maximum reading should be 18 volts. Why? Because the range of the galvanometer is 18 volts, right? So range is already given to you. So what you have to do, you have to calculate this series resistance R, right? So we know that from Ohm's law, now what is the total resistance of the galvanometer? How they are connected? They are connected in series or they are connected in parallel? So we have discussed this multiple times today, right? In objective, in discussion, right? So here they are connected in series. So they are connected in series means equivalent resistance will be R plus 12. Right, R plus 12. So from Ohm's law we know that V equals to IR. So V is here 18, I is 3 milliampere and R is R plus 12. So whenever you see milliampere, you have to convert it into ampere, or R plus 12 equals to 18 divided by 3 times 10 to the power of minus 3. So here it will be 3 6 18, so it will be 6000. Why 6000? This 10 to the power of minus 3 will go up and it will become multiplicative. So multiplicative means 1000, 10 to the power of 3 means 1000. So or R will be 6000 minus 12, it will be 5988. Yes, 5988 ohm. Okay, so 5988 ohm will be the required resistance in series. Okay, so how will you convert? You have to write it in the answer. You have to connect. We need to connect a 5988 ohm resistance in series with the galvanometer. Okay, with the galvanometer. That is the answer. Or if you explain that in the first, that let us suppose we add R value resistance in series with the galvanometer, then after that if you calculate R, that is also fine. Or you solve it and at the end if you add, that is also fine. Next, state and explain Biot-Savart law. This is a 3-mark question, by the way. So we have moved into 3 marks question. State and explain Biot-Savart law with a suitable diagram. So first you have to draw this diagram. Now you have to mention that the magnetic field at P due to the current carrying infinitely long wire PQ is given by magnetic field dB, small magnetic field due to this element, a small element dl at a point P is given by dl is proportional to, dB is proportional to the length of the current carrying conductor, length of the current element, dB is proportional to the current, dB is proportional to the, this 1, 2, 3, inversely proportional to the distance, and 4, dB is inversely proportional to the sine theta. Okay, combining we can write dB is equal to I dl sine theta by r mu naught by 4 pi. Mu naught by 4 pi is the constant, so I dl sine theta by r is the way you can calculate the magnetic field at any point. So this is the Biot-Savart law. This much you have to write in your annual exam. Now next question. Derive an expression for angular frequency of revolution for a charged particle moving perpendicular to a uniform magnetic field, or obtain an expression for the radius of circular path taken by the charged particle moving perpendicular to the uniform magnetic field. So both are a common question. So we have done this derivation once. So when magnetic field and velocity are in perpendicular direction, okay, we know that particle will move in a circular path. Okay, cross means into the page, dot means out of the page, so in this case it will move in this direction, magnetic field force. Right, now what will happen to this, we know that whenever there is a circular motion, mv square by r is given by the magnetic force. That is, what is magnetic force? Magnetic force is Q VB sine theta. Now because they are in perpendicular direction, so sine theta will be sine 90, sine 90 is 1, so we can simply cancel that. So so now what we will do, first we will do the find the angular velocity, angular speed. So for that we have to calculate v square by v equals to qb r by m. Okay, what we have done, we have taken v square, all the terms with v on the one side, all the rest of the terms on the other side, right? qb was there and this r multiplied, this m getting divided. Clear? So v is cancelled. Now what is angular velocity? Angular velocity is given by omega. Right? Now we know that v is equal to r omega. V equals to r omega. This is a thing that we have learned in our rotational motion chapter. So v equals to r omega. So r omega is equal to qb r by m. Now this r cancels. So we can say angular frequency is qb by m. Now as you can see, this is independent of the radius of the rotation. So even if you change the rotation for angular frequency, it is only dependent on b, q and m. Okay, it is independent of the value of r. Now what is the value of radius? To calculate radius, again we have to use the same method. mv square by r is equal to qvb. Okay, now here we are trying to find this radius r. So r equals to mv square divided by qvb. Okay, vv cancels, so r equals to mv by qb. This is the expression for radius. Just simply if you write this, you will get full marks. And try to draw one diagram and explain the terms. Okay, this is the centripetal force, this is the magnetic force. Now in equilibrium both force should be equal, so from there you have to derive at this relation. Okay, so this 1-2 line you have to write. Okay, so please, because the derivation is very simple, very small, you have to write these two equations and explain it little bit. Okay, I hope that helps. Next, 23, what is Lorentz force? Write its expression and explain the terms. So Lorentz force is when a charged particle is moving in a region of magnetic and electric field, it will experience a force known as Lorentz force. Okay, so when a particle is moving in a region containing magnetic and electric field, both the particle experiences a force. That force is called Lorentz force. Okay, now the expression for Lorentz force is F equals to QE. Now they have not asked you to write in terms of vector, so you can write in terms of scalar as well. QE QVB sine theta. Okay, so Q common E plus VB sine theta. Here you have to mention F is Lorentz force, E is electric field, okay, B is magnetic field, Q is charge, and V is velocity, theta is the angle between B and V. Okay, so this is the things that you have to mention to get full marks. In case if you miss any one of them, you will there will be marks deduction. So for this definition you will get 1 mark, to write this expression you will get 1 mark, to declare all the variables you will get 1 mark. So in case you make any mistakes, okay, either they will deduct full marks, or maybe if the teacher is considerate, they can give you full marks. Okay, 1 mark, 1 full mark. Full marks means 1 full mark. Okay, so if you make any mistakes, if you don't write it at all, they will definitely deduct 1 mark. Okay, if you write some of them but you forgot one of them, then maybe they will consider and give you 1 mark for that. Okay, now how can a galvanometer converted into a voltmeter? Explain with diagram. A galvanometer is converted into a voltmeter by connecting a suitable high resistance in series with it. So galvanometer, this is the most commonly asked question from this chapter. These are the one of the most commonly asked question from the chapter. Now what you have to do, suppose the galvanometer current is Ig, okay, then V equals to you have to write this equation. V equals to G plus R times Ig. Okay, so this is the thing that you have to remember, or from here you have to find the value of R. Okay, so G plus R equals to V by Ig, or R equals to V by Ig minus G. Okay, the same thing that we have used to calculate the formula in the problem that we solved, right? This is the formula. You have to write this formula starting from here. How we arrive this formula? So V is the potential drop across the galvanometer. So the potential drop across the galvanometer is V. Now from Ohm's law we know that V is equal to IR. So I is Ig, that is the galvanometer current. There is a maximum possible value of the current that can pass through a galvanometer. That current is generally represented by Ig. Okay, if the current fluctuates and if the current goes more than Ig, then the galvanometer will burn. Okay, it will stop functioning, it will stop working. Either they will have a fuse inside the galvanometer, so that fuse will burn and prevent the galvanometer from burning, or the galvanometer, if there is a cheap galvanometer, the galvanometer will not work at all. Okay, so there is a maximum value of Ig that can be allowed to pass through a galvanometer. Okay, now based on how much voltage you want to measure, you have to adjust this resistance. This voltage is the voltage that you want to measure. For example, in the problem that we solved, this V value was 18 volts. Okay, it can be 18 volts, it can be 100 volts, it can be 1000 volts, but based on the value of this V, the value of R will change. Okay, so the value of R will depend how much voltage you want to measure and how much maximum current that galvanometer can have. Okay, so based on these two factors, you can calculate the maximum resistance to convert it into a voltmeter, right? So this is the question. Next question is, how can a galvanometer be converted into an ammeter? Explain with diagram. So this is also very important question. So in this case, what we will do, there is a G and we apply a shunt resistance, a low value resistance called shunt resistance through the parallel to the galvanometer. So galvanometer is converted into an ammeter by connecting a suitable low resistance S in parallel called shunt with it. Okay, so this is the main thing. So this is called shunt. So now in this case what happens is, suppose the current, maximum current coming towards the galvanometer is I. Now when the maximum current that the galvanometer can measure as an ammeter, now they have changed it into an ammeter. Okay, so that current is I, but the galvanometer can accommodate only maximum possible current Ig. It will not accommodate any other current than Ig. Many students just remember the diagram without understanding it. That is the main problem. Okay, so the galvanometer can have maximum current Ig, so this current will pass through the galvanometer. Whatever the rest of the current, that current will pass through this shunt resistance, that is I minus Ig. Okay, so now these two are connected in parallel. So in parallel combination means the voltage drop between these 2 points is constant. So voltage drop according to the shunt resistance is I minus Ig times S, right? V is equal to IR, I is this, R is this, so this is the voltage drop according to the shunt. Now according to the galvanometer, this is given by Ig times G. Okay, so just the name of the resistance R is now changed. Resistance R for shunt is represented using S, and resistance for the galvanometer we representing using G. This is the common thing. Many students think what is G, what is S. So G and S are nothing but resistance R, but their name is different in this case because this is a specific case. Now what we are trying to find, we are trying to find this shunt value. Then knowing this unknown resistance is very important. So Ig times G divided by I minus Ig. This equation you have to write. Many students write the value of Ig. Okay, many students write the value of I minus Ig. I have seen many different students, they after doing this they try to find the value of Ig from this equation. No, because they have asked you how can you convert a galvanometer into an ammeter in this case. So in that case you have to find how much resistance that you have to apply to convert into an ammeter. Okay, so in this case the resistance is connected in parallel so that the current through the galvanometer remains the maximum value. Whatever excess current, that excess current will pass through this shunt. Okay, that is why it is called shunt. Shunt means when the current excess amount of water, excess amount of anything that can be bypassed. Okay, so basically excess amount of current is bypassing through this. So this is the value of the shunt. So you have to remember and don't mess it up. Don't mess it up. This is a very common question, and according to my understanding, one of these question is very likely will be coming to your not only your PU board exam but also your selection test or pre-board test, whatever you call it, coming January. Now state Ampere's circuital law and arrive at the expression for the magnetic field due to a long straight current carrying conductor. So what is Ampere's law? Ampere's law states that current through a closed loop, magnetic field due to a closed loop is given by B dot dl equals to mu naught I. Here I is the current enclosed by this loop. Okay, this is the Ampere's law. Exact statement you can check it in your book and write it down, but this is the main statement. Now they have asked you to find the expression for magnetic field due to a long straight current carrying conductor. This came once in your previous year. Okay, but this is a very easy derivation, so that's why I am doing it. Okay, you should also prepare for easy questions which may not be very common but they might come in your exam. Okay, so there are two types of strategy. First strategy is the most expected questions, you have to prepare them. Second, once you are very confident about the expected questions, you have to prepare at least few backup questions, okay, from each chapter. Okay, this is a backup question in case the question paper question setter decides I will not give you any common questions but I will give you easy question. So this is an easy question, okay, but the question is not common. Okay, I think similar things happened in your PU1 exam as well. Some of the questions were easy but they were not super common, so students were struggling, especially in biology if I remember correctly. Okay, students were struggling because the questions were not super common but it's important, right, and easy also. So B dot dl in this case is mu naught I, right? Now let us consider this loop. Okay, if you consider this loop, this is a circular loop, so it is circular symmetry. If the magnetic field here is B, magnetic field here will also be B, magnetic field here will also be B. At any and each and every point magnetic field will be B because this current carrying wire is very long. Okay, and it's a circular symmetry. For circular symmetry, any point on the circle it will be same. So first you have to construct a Amperian loop such that this current carrying wire is on the axis of this loop. Okay, now we will apply this Ampere's circuital law. So what is that? B is constant, so B will come out of the integration. Now integration of dl mu naught I. Okay, so B times, what is dl? Dl is the, if you take small dls and if you add them, then you will get integration of dl, right? That is the meaning of integration. So addition, so if you take all such small dls, then you will get the total perimeter of the circle, right? So the total length should be the perimeter. So B times 2 pi r is the perimeter equals to mu naught I. Okay, so B equals to mu naught I by 2 pi r. This is the expression, or you can simply write this as mu naught by 2 pi I by r. This is the expression for magnetic field due to a straight current carrying wire. Okay, so this is very simple. As you can see, this is very simple, very small mathematics, nothing difficult, no rocket science here. So this is an easy question, right? Now next 5 mark questions. Derive the expression for magnetic field at the point on the axis of a circular current loop. So this is the one of the most asked question, along with one more question. I will share that as well. So this is the most expected question from this chapter. So what is this? We have a current carrying loop, okay, and we are trying to find the magnetic field at some distance p on the axis. To solve that, we have to use a small portion dl, and for that portion dl we will find the magnetic field. Okay, now here we know that from this is the Biot-Savart's law. We all know there is a mistake I have made. Biot-Savart law will be r square here. Okay, also during the statement of Biot-Savart's law there will be r square. Let me correct that quickly, right? So the small magnetic field due to this current carrying element, this is a current carrying loop carrying current I. Okay, we are trying to find magnetic field at this point P, and the small magnetic field due to this small element is given by I dl sin theta by r square. Now here the angle between this current element and this direction vector will be 90 degrees. So theta is 90 degrees. So dB will be basically mu naught by 4 pi I dl by r square. Okay, now this magnetic field will make an angle theta, okay, and that angle say angle phi, okay, and that angle will be, this angle will be phi. If this angle is phi, this angle will be phi, and as you can see, for each component, each magnetic field, suppose this is dB, okay, vectorially. Now there will be a perpendicular component and there will be a component along the axis. Now if you consider another component here, okay, so there will be a magnetic field in this direction and there will be a component in this direction. They will cancel each other. So they cancelling each other means we only need to consider this component. So if this is dB, what is this component is? This component will be dB cos theta, cos phi in this case, sorry. So now some books use theta here as well, theta here as well, which in my opinion is not correct. So you have to use only phi, right? Now this radius is r, okay, this distance is x. You have to be careful when you are mentioning all these values, right? This will be square root of r square plus x square. Okay, so this is the value. Now here you have to write the actual dB dash, that is dB cos theta, cos phi. Okay, so what is cos phi here? Cos phi, you can see this is r, by the way. So this is the r for the this r as well, right? Now you have to remember the steps one by one. First you have to insert the value of cos phi. So from this triangle you can find the value of cos phi. So this the radius is r, okay, this radius is r, okay. Now if you see this triangle, for this input angle phi, this is the base, right? This side is the base. So this is the base means what? Cos theta is base by hypotenuse. So base is r. So cos phi is equal to base by hypotenuse, that is square root of r square plus x square. Or you can say it is nothing but r divided by r square plus x square to the power half. Okay, square root means to the power half, so we will put that value here, r divided by r square plus x square to the power half. Okay, so this is the value of dB dash. We are interested in calculating this dB dash only. This is equals to dB dash. Okay, if you draw this diagram properly and explain all the terms inside the diagram, then that saves you a lot of time. Without explaining the proper terms, you can still proceed with the derivation, right? That is the most important thing. Now what is dB? dB is this, mu naught by 4 pi times I times dl times r square. What is r square? R square is r square plus x square whole root. So square of that will be r square plus x square, right? So r square is simply square root of the square of this, so square root will go. Now there is one more term, r divided by r square plus x square to the power 3 by 2, sorry, to the power 1 by 2. Now I have this privilege to do it in my class, but you have to do it in your when you are writing, you have to do it on your hand. Right now let us multiply these two terms. Okay, when we multiply these two terms, this r we can write it here, and r square plus x square, r square plus x square to the power half will be combined, and we can write them as to the power 3 by 2, and there will be an r here. Clear? So this is the expression for dB dash. Now what we will do, we will find the value of b. Okay, b dash or b, right? Let me erase this. So when we take the component all such dls, if you take all such dls and do the integration or add them basically, then you will get the magnetic field b dash. So magnetic field b dash is basically integration of dB dash. Now if you see in this expression, everything is constant except dl. I is constant, r is constant, x is not changing, this r is obviously constant, mu naught by 4 pi is definitely constant. So everything is constant, that is there is no variation in them. So all the constant terms for integration definitely come out of the expression, right? So here will be I r by r square plus x square to the power 3 by 2 times integral of dl. Now what is the integral of dl? You already know that dl means if you take all the small portions, so that will be the perimeter of a circle. So perimeter of a circle is nothing but 2 pi capital R, right? 2 pi capital R. So now you can cancel them, it will get 2. So you will get here b dash equals to mu naught by 2 I r square by r square plus x square to the power 3 by 2. This is the general expression. Now if they ask you one more side question, that now calculate the magnetic field at the center of the circle, so center of the loop. So if they ask you to find the center of the loop, for the center, okay, x equals to 0, because this is x, so for center x will be equals to 0. So only thing that you have to do, you have to put x equals to 0, and you will get b dash equals to mu naught by 2, you will get I by r. Okay, this formula is important to remember for competitive exam, important for derivation as well. Okay, so this is the same general method to find the magnetic field at the center, at the loop, on the axis of the loop, and this is the special case where you are finding the magnetic field on the center of the loop. Okay, now next question, derive an expression for force per unit length on two infinitely long thin parallel straight conductors carrying current, hence define ampere. This is the second most important question. Okay, every alternate, in fact this question has come more than the other question. Okay, the other question, if that question is coming twice, this question is coming thrice. Okay, and this question is most important for your year. Why I am saying that? Because in 2024 exam circular loop was there. Okay, so I am expecting, according to my understanding, that they generally don't repeat exact same questions every year from this chapter. So there is a high chance that this question will come in your year. Okay, in 2024 exam, this and that both were important, because in 2023 some other question came. Okay, 2022, sorry. So 2023 some other question came. That's why this question, both of the questions were important in 2024, and out of that circular loop came in 2024. So highly probably, highly likely this question will come in your board exam. Now for that, first of all you have to draw two parallel wires carrying current infinite, so you can add some dots into it. Okay, suppose this is wire A, this is carrying a current IA, this is carrying a current IA, this is a wire B, this is carrying a current IB. So what we have to do, first we have to find the magnetic field, and the distance between them is D, and we have to consider, suppose we are considering a length of the wire, imaginary length, say L. At the end we have to divide this L so that we can eliminate this term. Okay, now if you remember, we have already find the magnetic field due to a straight current carrying wire at a distance R, right? So what was the expression? This one, right? So magnetic field due to a straight wire is mu naught by 2 pi I by R, right? So now let us apply that. So magnetic field due to this current carrying wire at this distance is given by mu naught by 2 pi IA by D. Instead of R it will be D. Now similarly, magnetic field due to this current carrying wire here will be mu naught IB 2 pi by D. So this is the magnetic field due to this current carrying wire at this location. This is the magnetic field due to this current carrying wire at this location. So both will have magnetic field, but they will influence each other. They cannot influence themselves, right? I cannot check my own marks. Someone has to check my marks. So whoever is checking my marks, I can check their marks, right? Just for an example, right? So basically what is happening here, they are mutually exchanging this. So now what you have to do, force magnetic field due to current A is given by mu naught by 2 pi. I think there was no 2 pi. There was a 2 pi. Right? So mu naught by 2 pi I by IA by D. Okay, so what is the force on B due to A? What is the force acting on B due to A? So we know that that is nothing but B I L, Bill sin theta. Theta is 90 degree in this case, so B will be in this direction, current is in this direction, so they will definitely 90 degrees, so we can ignore the theta part. Now why I have written it like that? Now when we are calculating the force on B due to A, first is magnetic field B. So what is the magnetic field at this location? Magnetic field at this location is BA, right? And what is the current passing through the conductor B? So that will be IB. Okay, and what is the length? We are considering the length to be small l, so BIL, right? So this is the force on B due to A. Or let's put the value of BA, it is mu naught by 2 pi IA by D times IB times L, or mu naught by 2 pi IA IB by D times L. Now what is similarly the force on A due to B will be the same value, okay, because in that case the magnetic field will be BB and current will be IA, right? So you can calculate that and you will get the same value. Okay, because it's symmetric, we can simply say force on A due to B will also have the same value due to symmetry. Therefore, force per unit length is given by mu naught by 2 pi Ia Ib by d. So this L is divided here. Okay, so L is gone. So you have to remember about this small change, small trick. If you don't do it, they will deduct 1 mark for this. Okay, so once I was teaching in a college, there the topper of the class, he make only one mistake of dividing without dividing this. So I had to deduct 1 marks, and he was about to get out, but he got 1 mark less because of this small mistake. Okay, so you have to, don't be like him. You have to remember that you have to divide it by this, and you have to score full marks, right? Now, so this is the case. Now, how can you define ampere? To define ampere, first of all, you have to understand what is ampere. Ampere is the current, right? So if Ia equals to Ib, both of them are 1 ampere. Okay, their distance between them is 1 meter. Okay, let's insert those values. So force per unit length is basically mu naught by 2 pi, right? So force between them is mu naught by 2 pi, because this both of them are now 1. Okay, 1 times 1 divided by 1, so they are all gone. So this is the force. Now what is mu naught? Mu naught is 4 pi times 10 to the power of minus 7 divided by 2 pi. So force per unit length will become 2 times 10 to the power of minus 7 Newton. Okay, so Newton per meter. Okay, so force per unit length will be 2 times 10 to the power of minus 7 meters. So from the definition, you can say that ampere is the current when flows through each of the two parallel conductors kept at a distance of 1 meter experiences 2 times 10 to the power of minus 7 Newton per meter force. Okay, so this is the definition of ampere from this law. So if you miss that also, they will deduct 1 mark. Okay, so finding the derivation is, first you have to write draw the diagram, 1 mark for that. Then you have to calculate the magnetic field, both magnetic fields, for that 1 mark. Okay, then you have to find both the forces. Okay, and then final expression for that 1 mark. Okay, and then for the definition of ampere, 1 mark. So 5 marks for that. Okay, so you have to write each and every step without missing. Now, with the help of a diagram, derive the expression for torque on a rectangular loop placed in an uniform magnetic field. So uniform magnetic field, this question came in 2023. Okay, so that question I was talking about, there was a question which never came in, only once this question came. So you have to, just for practice, you can remember that. So if you place the current carrying wire, okay, in a magnetic field, now as you can see, if this is a current carrying loop, okay, rectangular coil, then this and these currents are parallel or anti-parallel to the magnetic field, so there will be no force acting on this. But here, okay, suppose this length is breadth, suppose this length is L. Okay, so then, and the distance between them is, say, B. Okay, distance between them is B. Now for one loop it will experience a force, one loop it will experience a force in this direction, and other loop it will experience a force in this direction. Okay, and what is the magnitude of force? Suppose this is arm 1, this is arm 2. So force on arm 1 is Bill sin theta, and as you can see, the angle is either 90 or 180. So both cases it will be plus 1 only. So magnitude of the force is Bill. Similarly, this is also equals to F2. Very simple small derivation. Okay, so F1 equals to Bill equals to F2 magnitude wise, right? So what is the torque? Torque we know is when two equal and opposite forces acts on a system, okay, the torque is given by any one magnitude times the distance between the forces. What is the distance between the forces in this case? Distance between the forces is B. And here as you see, the forces are opposite in magnitude, because if one is in this direction, other one is other direction, so definitely there will be a torque acting. So let's say F1 times the distance between them. So what is F1? F1 is BIL times B. Okay, now what is L times B? L is length, B is breadth, so L times B gives the area. Okay, so BI times A. Okay, or AI times B. Now what is IA or AI? So far we have also encountered this quantity multiple times. AI is basically the magnetic moment. So this is MB. Okay, so this is the torque. Now in terms of vector, this is given by M cross B. Okay, in terms of vector notation, this is the expression for torque. Very simple small derivation. Okay, but again uncommon question. So even though it is very simple and small, if you are not prepared, you will not be able to answer this small question. Now the next question is, what is the principle behind the working of a moving coil galvanometer? Write the help of a neat level diagram, obtain the expression for the angular deflection produced in moving coil galvanometer. This question never came, but this question is included in your sample question paper, model question paper, latest 3 model question paper. One of them includes this question, so I have given this question as well. So many students are struggling to write the principle. What is the principle? And this question is least likely to come. Okay, so this question you can expect that this question is mostly not coming, but what's in a harm if you just study one extra question, right? So just go through it once, in case diagram is slightly complicated but not super complicated. There will be a spring here, there is a circle here. Okay, this is a south pole, north pole, and this arrow. Okay, pointer, paramagnetic magnet, permanent magnet. Obviously both sides there will be permanent magnet, so there will be magnetic field, uniform magnetic field, and this is the diagram. Okay, you can remember this diagram or you can draw on your own. Okay, different books provide different diagrams, but principle is, when a current carrying coil is placed in an uniform magnetic field, it experiences a torque. Okay, so that is the basic principle of the galvanometer. Now what was the torque? We already calculated for that. It is B MB. MB is the torque acting on the system, M is the magnetic moment. Now in case of normal coil, it is IAB, right, for a single loop. Now because for a galvanometer there is not one loop, there are n number of loops, capital N number of loops present in case of a galvanometer. So what we will do, we will include that n here. Okay, so this is the NIA. I told you magnetic moment is given by NIA when more than one loop is involved. So torque acting on this is NIA. Now here in case of galvanometer, there is a small spring involved. So you see, this is a spring. Okay, now this spring has a spring constant K. If the spring constant is K, okay, and the angular displacement, initially it was like this, okay, and the angular displacement is theta, angular displacement is theta, then we can say that torque acting on that is given by spring constant K times theta. This is the formula. Okay, you can remember in your from your previous classes, or you can remember it now. So we are trying to find this theta, that is NIAB divided by K. So this is the basic relationship of the galvanometer. Galvanometer, basically if you change the current I, you can change the angle theta. Generally B is due to the permanent magnet, so B is constant. Number of turns in the galvanometer is also constant, right? You cannot change, you cannot always open the galvanometer and change the number of turns, so number of turns is constant. Area of the armature coil, that is already set up inside, that is also constant. Magnetic field is constant because of the permanent magnet. K, that is the spring constant, is also constant because it is already there inside the galvanometer. Only thing that you can change is this current. Only thing that you can change is this current. So basically you can see that this angle theta is directly proportional to the current I. Okay, sometimes this is written as GI. This G is not the galvanometer resistance, but this G represents the constant of the galvanometer. G is nab by K, nab K. Okay, so this G is known as the galvanometer constant. Particular for a galvanometer, given galvanometer, this is a constant value. So this is how, this is the basic formula. Okay, you can leave it here. In your book they have left it here. You can go one more step and you can define this. Both are fine. Okay, so this is a new question, and I hope you enjoyed the entire lecture. I'll be back with a new chapter on Tuesday. Till then, bye.